Good morning. So this is the 13th lecture on computer control. I hope you are not superstitious. So we were speaking about designing a controller by doing feedback of the state and placing the poles of the controller system. So what is the idea? The idea is that you assume that you know the state model of your process that you want to, the process that you want to control, which is x of k plus 1 equal to some matrix phi times x of k plus some vector gamma times uk assumed constant. And your feedback law is a feedback from the state. So it's a minus. This minus is not essential, so we put it just because feedback is usually recognized as negative. Okay, so we put the minus here. If we had no minus, then the L that we want to design would be with the opposite sign. And so U is a linear combination of the elements of the state. So L is a row vector of coefficients, of gains, and X is a column vector. So minus Lx is nothing more than a linear combination of the states, and you want to compute the coefficients of this linear combination such that the closed loop system has poles in the desired positions. So how do you compute the closed loop system? Well, you plug this feedback control law into the open loop model. So we replace U by minus Lx. And this is the state model for the closed loop. X of k plus 1 equals to phi minus gamma L times xk. Okay? So the new matrix of the dynamics in closed loop is no longer phi, but it's phi minus gamma L. And you want to select L such that the eigenvalues of this matrix, which are the poles of the closed loop system, are in prescribed positions. And we said, well, we can just compute the characteristic polynomial of the closed loop system. So it's the determinant of Zi minus phi minus gamma L, which is Zi minus phi plus gamma L, and equate it to a vector, to a polynomial which is the desired characteristic polynomial. So alpha c as roots, the desired poles. So you select the desired poles, your specification is in the form of desired poles, and you have to solve this equation. Okay? So one possibility is to equate the coefficients of both polynomials, one in the left that depends on L, and the one on the right that as roots the desired poles. This is the method of unknown coefficients. And by equating these coefficients, what you get is a system, a linear system of equations satisfied by L. Then I told you that it's possible to solve the problem using some formulas. One is Ackermann's formula, which is given in this way. So this matrix C is this polynomial of matrices here. Okay, and sorry, this matrix C is the controllability matrix, and the controllability matrix is nothing more than picking up the open loop model and writing the vector gamma, then matrix phi times gamma, which is again a vector, and so on, up to n minus 1, where n is the order of the system. So for a single input plant, this has n columns, because you start at phi up to 0 and go up to phi of n minus 1, and n rows, because it's the dimension of gamma. So it's a square matrix, and provided that the rank of this matrix is non-zero, that is to say, provided that all these columns are independent vectors, then you can, the matrix is of course invertible, and you can place the poles where you want, at any position that you specify. And in Ackermann's formula, the controllability matrix appears as the inverse. So if the system is what we say controllable, this inverse exists. And I also told you that for practical purposes, this formula is implemented in MATLAB in the function akka, and you can also use the function place. They do the same computation. Basically, what you do is you give the matrix phi, the vector gamma, and also a vector with the desired poles, and it computes the vector L of gains. The difference between place and Acker is that place is numerically more sophisticated, so it allows higher order systems to be designed, and also multivariable systems, which is something that we are not going to be concerned with here. Now, the problem here is that we don't have in general access to the state. So the strategy is design a state estimator, and use the estimate of the state to do the feedback. So instead of feeding back the true state, we are going to feed back the estimate of the state. So how can we design a state estimator or an observer? Okay? So one possibility is a so-called prediction observer. What is the prediction observer? You can look at here. Okay, so this is nothing more than a replica of the system. Okay, this first part is the replica of the system plus a correction term. Now, I'm writing this in a funny way. Why? Because you should read this in this way. So x hat, the hat means estimate of x. So the estimate of x at time k plus 1, and this vertical bar means given. So the estimate of x at time k plus 1 given the information up to k is equal to phi x hat. So the previous estimate, the estimate of x at time k, given information at time k minus 1, plus gamma uk, okay? And if you replace x hat by x of k plus 1, and here x of k, and so on, so these first terms correspond to nothing more than a replica of the system. So driven by the same input. So what you are doing is, if you forget this term, is that you are replicating your system with the same input. So if the system, if the model is perfect and there are no disturbances, if you apply the same input to the true system and to the model, you will get the same state. Now, the problem is that in general, there are disturbances that affect the system and do not affect the model, of course. And you may not also know the initial condition of the state, of the true state. So your initial condition for the estimate of the state can be different. So we add this correction term. Okay? We add this correction term. And this K naught is a vector. And what is between these curled brackets? So it's a difference between y of k, and you see, this is what you expect y of k to be given your previous estimate. Now, to compute the estimate at time k plus 1, you are using yk. That's why I write here x hat of k plus 1 given the information up to time k. Okay, so this is why this is called a prediction observer, because you are making a prediction based on the information up to time k. Now, I could have justified why does this work. Basically, what you do is that, of course, there is a mathematical justification, but in an intuitive basis, what you are doing is you are passing, when you don't have this term, when k0 is 0, so this last term is not present, you essentially have an estimate which does not depend on the data apart from you. So it's a kind of open loop estimate. And if x deviates from or if x hat deviates from the true state x, there is nothing in the formula that tells you that you should do a correction. Instead, when you add this term, if x hat deviates from the true state x, then this prediction of what yk should be will grow. And by growing, you will, if everything is all right, you will create a correction term in the estimate of x that drives you again to the state. Okay? So this formula provides the definition of a block called state estimator or observer that has as input y and u, and as output a vector of estimates x hat. Now, let's be a little bit more precise. Define the estimation error x tilde as the difference at a given time between the state and the estimate of the state x hat. Now, write the equation verified by x, which is the plant model. X of k plus 1 equals to phi x of k plus gamma u of k. Now, write the equation of the prediction estimator, and which is what we have just seen. And if you subtract these two equations, well, this term gamma u cancels out, and you use then the definition of x tilde, and you end up by canceling a number of terms. Use also the output equation, so remember that yk is cx of k. So by using this, you end up with this equation verified by x tilde. When you study this slide, it's interesting that you do all these computations in detail, which is very simple. Now, you end up with this equation, which is x tilde of k plus 1 equals to phi minus k naught c x tilde. Okay? And the solution of this error equation is nothing more than starting with the initial error and going on multiplying by phi minus k0c, okay? Where c is the output equation. So c is this function, okay? C is the matrix that appears in this output equation. So y is c xk. Don't get confused with the controllability matrix, which is another story. Okay, so for x tilde to go to 0, and if x tilde goes to 0, x hat approximates x, then all the eigenvalues of this matrix phi minus k0c must be smaller than 1. Okay, Think of the scalar case. If in the scalar case, this is not a matrix, this is a scalar, and this value, the absolute value of this, the absolute value of this phi minus k0c, which is a constant, must be smaller than 1. Must be between, the value of phi minus k0c must be between -1 and 1. Okay? Because in that case, you are computing the powers of a number between -1 and 1, and this goes to 0. If this is a matrix, then you can expand this as a sum of powers of the eigenvalues of the matrix. So the modulus of all the eigenvalues, I represent the eigenvalues of this matrix in this form. So lambda of phi minus k naught c, so to say that lambda is an eigenvalue. So all the eigenvalues must be, in modulus must be smaller than 1. That is to say, all the eigenvalues must be within the unit circle. Okay? So you should design this vector k0 such that all the eigenvalues are at prescribed positions within the unit circle. Okay? Actually, you can specify the eigenvalues in a polynomial A0 or AO for the observer. This is O for observer, not 0, of Z equals to the determinant of phi minus KOC, okay, this matrix here. And then you equate the characteristic polynomial of matrix phi minus k naught c and AOZ, as we did before. Okay, and provided that the pair phi c verifies some conditions, then you can select KO such that the error goes to 0. So such that you can place all the eigenvalues at arbitrary positions. So you can select AO as you wish. You can select the roots of AO in arbitrary positions. So if these positions are inside the unit circle, what happens? You can see here a plot. This is the empty bullets are the samples of the state, and the crosses are the samples of the estimate of the state, so of x hat. And initially, you start with some error. Okay? That's your first estimate of the error of the state, and then the error, which is dark line, is decreasing, and you are approaching. So the estimate approaches the true state. There is a transient in the error, and then you go. And the fastest this goes to 0 depends on the selection of the roots of the desired characteristic polynomial, exactly as we did in the controller case. Let's see one example. Consider again the double integrator that we have considered before to design the controller system. And we want to design a predictive observer such that roots of the polynomial observer are placed at 0.4 plus minus j 0.4. So I built a polynomial with the desired roots. So AO of Z is the desired characteristic polynomial, and the roots are exactly, let's go to the previous slide, 0.4 plus or minus j 0.4. Now, I also built this characteristic polynomial of the matrix phi minus k KO C. Okay? So I have here Z times the identity minus phi plus vector k, KO, and C, which is 1, 0. Remember that C was given. So I'm observing the first component of X. Now, if I do all these computations, which takes 1 or 2 lines of computations, then I end up with this characteristic polynomial. So this is the characteristic polynomial of the error dynamics. So the error dynamics is this equation here, okay? This equation here satisfied by the error. And this is the matrix of the dynamics of the error, or error dynamics, okay? So the characteristic polynomial of the error dynamics in terms of general values for KO are given here. Now, what am I going to do to design KO1 and KO2? I'm going to equate the coefficients of this polynomial to the coefficients of the desired characteristic polynomial. So I say that minus point h should be KO1 minus 2, and h KO2 plus 1 minus KO1 should be 0.32. Okay, which gives me these two equations. Then I solve these equations and I get the values of KO1 and KO2. Now, let's go back to the control problem. And now instead of designing a state feedback, I replace the state by an estimate of the state. So I add the equation for the observer, and by iterating this equation, I'm generating x hat. And then my control law is a feedback of x hat. Okay, so at time k, my uk is minus L x hat of k given observations up to time k minus 1. Okay. Now, the funny thing is that the closed loop poles are the eigenvalues or are the roots. The closed loop poles are the roots of these two polynomials, determinant of zi minus phi plus gamma L, which is nothing more than the poles you would get if you were feeding back the state, not the estimate of the state, but the state, the true state, and phi minus KOC, which correspond to the eigenvalues of the state estimation dynamics. Okay? So the conclusion is that you can design your controller assuming that you are actually feeding back the state. And you have no state observation. Then design an observer, assuming that you have no control, and you design your observer, so the gains for your observer. And the poles of the closed loop system, when you replace x by x hat in the control law, so the state by the estimate given by the observer in the control law, are nothing more than these two sets of poles. That's the principle of separation. So you can design separately as if they were not, there was no interaction. The controller based on phi and gamma, matrices phi on gamma, and the observer based on phi, matrices phi and c. Okay? Any question at this point? No. No. Maybe you can do a little bit better. Okay, so by using the predictive observer, you have this nice property because you can design and impose stability, and you can design separately both things, the observer and the state estimator. But maybe you can do a little bit better because you are relying you are making your state estimate to rely on not on the full data that you have observed. Suppose that your computer is very fast and the computation time to compute the state estimate from the observed data is neglectable. Okay, so it takes some time to compute the gains and to do all the computations. But suppose that at time k you observe yk and you want to estimate x of k. Okay, and then you do a feedback. Remember that in the previous scheme, we were relying at time k on the observation of y at time k minus 1. That's why it was a predictive observer. Now, you are discarding the last, in the previous scheme, you are discarding the last observation of y. So maybe you can incorporate it, and maybe this improves the quality of your design, in particular when we have disturbances. So you can have this problem. So instead of, let's go back to the equation of the observer. Now, if you replace k plus 1 by k, you get x hat of k given k minus 1 equals to x hat of k minus 1 given k minus 2 plus gamma uk minus 1 plus k naught y of k minus 1 minus c hat of k minus 1 given k minus 2. So you have here, remember, we have delayed everything by k, so I have here x hat of k depending on the previous variables. Now, let's try to write an observer based on the last observed value for y. So again, instead of writing the state at time k plus 1, I write it at time k to make things more obvious. So x hat of k, given observations up to time k, it's a replica of the system. So phi times the previous estimate, okay, plus gamma u previous control. Okay, this is nothing more than the replica of the system, and the system has delay 1, so here you cannot do anything. Now you would have ko, another ko, okay, this probably will be different, and you have yk, okay, then you should have x hat of k. So this is a problem because x hat of k is what you are trying to compute on the left, and you have it on the right. So what you do, you replace here x hat of k by the estimate of x hat of k given the previous state. So you replace, so you have y minus c, and then here, between here and here, you should have x hat of k, but since you don't have it, what you do is to use the model. So x hat of k is phi x hat of k minus 1 plus gamma u of k minus 1. Okay, and now you can actually you have an iteration because given the state estimate at time k minus 1, you can observe yk and do the computation of x hat at time k. Okay, so let me repeat. Suppose that you want to write x hat of k given observations up to time k, so given yk. So this first part is nothing more than the replica of the system. Now here we have the gain, and then y minus what y of k is expected to be. And y of k is expected to be c times x hat of k. But x hat of k, you don't have it. So what you do, you replace x hat of k by the model of the plant. So you replace x hat of k by phi x hat of k minus 1 plus gamma u of k minus 1. And this is the so-called current observer. That is to say, the observer that yields the estimate at time k based on the observations up to time k. Okay? So you have two observers in discrete time. The predictive observer, it's what we have studied before, corresponds to the situation in which my estimate of the state depends on the observations of y up to time k minus 1. Okay? Now, the current observer, the estimate of the state at some time k depends on the observations up to that time. Okay? And it's a little bit different. For the current observer to be applied, remember that you should be able to do all these computations here in a time which is neglectable with respect to the sampling interval. So if you have a sampling interval of, say, 1 second and a computation time of 1 millisecond or 2 milliseconds, okay, or even less, then it's feasible. But if your sampling time is, say, 5 milliseconds and your computation time is 2 milliseconds, then you cannot apply the current observer. You have to apply the use the predictive observer. Okay? Notice also that the expression for KO will be different, okay? Because the error dynamics will be different in this case. You can find detailed discussion of the current, more detailed discussion of the current observer in the notes. There are some notes that I wrote, and they are in Phoenix. It's a companion to lab work. Now, how can we organize this as a block diagram using, for instance, simulating? Okay, we can write a prediction of the state based on the last observation, which is nothing more than a replica of the system, and we can have then a correction to update your prediction with the last observation. Okay, and you can show that these two equations are actually equivalent to the previous equation. So if you write the block diagram of these equations, then you have an input which is y, an input which is u, and you also have two outputs. This is x hat is the predictive observer, the estimate yielded by the predictive observer, and x bar is the estimate yielded by the current observer. So this is a practical way that you can use in your design of the design of your lab work to implement the observer. Now, what you do if you want to use the predictive observer, you multiply this by the controller gains and you feed it back to generate U. Okay, and of course, remember that this is just the estimation part. You have the this is just, let me go back a little bit to the beginning. This is just this green block. Okay, then you multiply by K and you estimate U that enters your estimate and also the physical process. Any question? Okay. Now, remember that yesterday I told you that we could design your solve your pole placement problem instead of imposing the poles by optimizing a cost, and the cost was the energy spent in the state and the energy spent by the controller. Okay. Now, also for the state estimator, you can formulate your problem as an optimization problem. Okay, and you assume that you have some noise. So our model now includes some noises, and you see this V1 and V2. Okay, this V1 and V2 are what? This V1 models disturbances detected on the system. This V2 models sensor noise. Okay, so this second equation models the sensor. I'm saying that the output is a linear combination of the state. Okay, so this models the sensors, and I'm assuming that I add some sensor noise. And these are white sequences. Okay, and they have powers. That is to say, the correlation, the autocorrelation or the covariance matrices, autocovariance matrices, QE and RE. So E for estimator, that's it, being this, because we have matrices Q and R for the controller to distinguish from them. Okay, so the higher these values, the more intense are these noise sequences. This is a noise in the sense that we understand that it corrupts information. This I also call it noise, but it's actually a disturbance. For instance, if you have aircraft and you have turbulence, you have some variation, not turbulence, but some variation in the atmosphere, then you can model this as a stochastic process that models the disturbance caused by the changes, the stochastic changes in the atmosphere as the aircraft flies. And the power of this disturbance is QE. Okay, if you have noise, the power of the noise V2 is RE. So the expected value of the square of the variable in steady state. Okay, this K is taken in steady state. Now, suppose that you want to estimate. Suppose that you want to estimate X given observations of Y. Okay, and you are going to impose two things. One thing is that your estimate is unbiased. That is to say, when you do a lot of observations, that the expected value of the estimation error is 0. So your estimate X hat fluctuates, but it fluctuates around the true state. That's an unbiased estimator. Now, to have an unbiased estimator, you should have the observer structure, either the predictive or the current. Okay, let's consider the current. Now, the second specifications that you do is that the steady state power, the steady state, better to say energy, because I'm summing up from 0 up to infinity, of the estimation error. So you have the estimation error, norm squared. Okay, remember that these are vectors. And then I sum for everything up to infinity, and I take the expectation of this value. So that's the power of the deviations. I want this to be minimum. So I want to select X hat such that this is minimum. Okay? And this second specification depends on the choice of the observer gain. This K0 KO that appears here. Okay, so this structure ensures that your estimate is unbiased. That is to say, that the expectation of the error is 0. If you compute the expectation of x hat minus x at time k, the expectation is 0. You can do a simulation, and you have x hat wondering about x, and if you compute the average, the mean value of the error over a long time, it's a value that is close to 0. Okay, if it would be for an infinite time, it would be 0. So for that, it's enough that you use this expression here, okay, that defines the structure of the observer. Now, if you want to minimize the power of the error, then you have to design KO. Okay, you have to design KO. I'm not going to give the expressions. This is the Kalman filter, and you can compute KO using the MATLAB function DLQE. Okay, don't forget the D, because LQE is the Kalman filter in continuous time, and DLQE is the Kalman filter in discrete time. Okay, so if you know QE and ERE, so if you know these noise variances, you select this. You can select the gains, compute the gains, such that this happens. Okay. Now let me give you some idea of what is happening. You have basically. Let's look again at the model. You have basically a system, okay, and you have. Let's think about this V2. Suppose that V1 is 0, but you have V2. Now, you can design a filter. A filter is something that is a dynamic system that lets the components, the frequency components of a signal to pass in some frequency regions, and it has a very low gain in other regions, so they block them. Okay, think of a low pass filter. Okay, so imagine that you have Y, and you compute X from Y, and your computation involves a low pass filter. Now, if you have some band, well, you are letting interesting components of X in that frequency range to pass, as well as noise. Now, go on enlarging the bandwidth of your filter. There is a point in which all the useful components of X have passed. Okay, so X is typically a low pass signal. So there is a moment or a frequency value after which all of the components of X in practice have go across the filter, are not attenuated by the filter. And if you enlarge it more, what happens is that you are not letting more X to pass, but you still have noise passing, because noise is a white noise. White noise has a constant frequency constant. That's why it's white. Okay, so its frequency, it's present at all frequencies. Okay, so you go on enlarging your bandwidth of your filter, and the optimal point is somewhere close to the situation in which all of the X's have passed. Because if you enlarge it more noise comes, which is a bad thing, and you win nothing because there is no more components of X to pass, because all of them have already passed the filter. Okay, so the Kalman filter does this in an automatic way. I'm not going to to write expressions here, but you can have these ideas. Now, one thing is you must know this QE and RE matrices. Okay, if you have just one observation, then this is a scalar. RE is a scalar. If you have several observations, this will be a matrix. Now, you can say, well, I'm going to make experiments on the plants and to estimate QE and RE. This is very difficult to estimate QE and RE. So another way of thinking about this, remember that what you want is not really to estimate the state, but it's to control the system. So use QE and RE as tuning knobs. Okay? So adjust QE and RE to improve the design of your control system, because remember that after this, after the state estimator, you are going to have a controller, and what you want is Y to be close to some reference according to a cost or something. So use QE and RE as tuning knobs. That's an idea. It's funny to mention that this idea took about 20 years, because Kalman filter was published in 1965, and it is perhaps one of the biggest inventions of electrical engineering of all times. And 20 years later, so around 85, 86, this idea of using the noises at tuning noises, so tuning parameters, so instead of trying to discover the true value, which is quite difficult, even impossible in a practical situation, so using this as tuning knobs of the controller. Okay, so adjust QE and RE when you have the controller. So it came 20 years. It took 20 years to understand that. Okay, so the last thing I would like to mention to you is the introduction of a reference. I'm just mentioning here one of the ways of introducing a reference. And you can see here, you have your process with input U, with output Y. And you build an estimator that receives Y and receives U and generates X hat. Then you do multiplication by the vector of controller gains. And don't forget a minus sign, which is here, so you generate U. Okay? So if you don't have this part on the left, this sign is 0. What you are doing is, if you designed properly your estimator and your controller gain KC, then you will have something that goes to 0. So if you disturb your process, your disturbance will be rejected, in the sense that Y goes to 0. You create a non-zero initial condition associated to the disturbance, and Y goes to 0. If you have a constant disturbance always affecting the system, well, okay, Y will do its best to be close to 0. But sometimes you want Y to track a reference. So you need something that takes Y from 0 in steady state. And for that, in general, you must have U taken away from 0 too. So what you do is you add a term, and the term is you pick up your reference R, and you multiply by a gain, and you add here. Okay? So your controller is no longer minus KCX hat, but is RNR minus KCX hat. Okay? Now, how can I select N? Can someone give me a hint? What should N be? You have here a linear system, okay? Suppose that I don't have n, I just put r. Do you think that y would be close to r? This is a linear system, okay? With all these computations here, it has a state here, a state here, so you have a state of dimension 2n, but actually this is a linear system. You can even write a transfer function. It might look complicated to you, actually it is not, but the essential thing is that between this point here, at the output of this n block, and y, you have a linear system with transfer function, let's call it gc of s, or gc of z. So if you add an r, what happens? Where is y going to be in steady state? Can you help me?
The r times the gain.
Times the gain, okay? So what should n be if you want y to approach r?
The inverse of such gain.
The inverse of the gain here, okay? Actually, you can, for instance, do some simulation, okay, and adjust by trial and error n. But you can also do it in. You can also do it by using some formulas that you can derive from the process model, okay? And this is in the, if you look at the lab guide, the formula is there. You don't have to know it by memory. What is important to know? Important to know is that n should be the inverse of the static gain of all this stuff here. Okay? Now, is this, you have studied feedback, okay? You have studied feedback. And is this a standard feedback system? What happens in a feedback system? In relation of y and r, what is the situation in a standard feedback system that you don't see here? Can you see? I'm putting some music to you. I'm not sure whether you can hear it.
Do you mean that the y is subtracted from r directly?
That's right. And here, do you see any subtraction here?
We do, but only after the estimation part.
So there is a stuff, you never compare y with r. So let's go back to the very first slide. So the very first slide, okay? In this very first slide, apart from this noise is nasty because it disturbs the comparison between y and r. What do? You compare y with r, and then you amplify it, okay? And if everything is okay, y should be close to r because this should be 0. Okay? If this is very small, if this is very high, for this to be a constant value, not very high and not very small, then this must be very small. Okay? So the higher the gain, the smaller the error, and y approaches r. That's the rationale for feedback control. The first guys who invented this in the 18th century already. Okay, so this is more than, it's almost 2 centuries and a half ago. Okay, and the guys, they knew very little about theory. The story of the S theory was invented by an electrical engineer. It was not Laplace who invented it. Okay, it was the operational calculus, came say about 100 years after the first feedback controllers that date back to the 18th century. And those guys who invented the feedback control, they were just thinking, well, I'm going to compare y with r and to build an error, and then I amplify it somehow, okay, to build your action. So if y is equal to r, I stand still. If y is bigger than r, so this area is negative, so I decrease. If y is smaller than r, this area is positive, so I increase the action. Okay, that's just this. Of course, you know that then you can have problems with stability. It does not always work. Actually, right in the beginning, stability was a problem. Okay, the first steam machines, the feedback was used to control the velocity of steam machines in the 18th century, and it was recognized that sometimes the scheme was not working. So there was a prize on a theoretical work that could solve the problem of stability. Okay, and you know who won this prize?
Lyapunov?
You know?
Lyapunov?
No, Lyapunov was not thinking control problems. Lyapunov was thinking of a problem of you have a rotating mass of liquid, and he wanted to study the stability of a rotating mass of liquid, like a planet, liquid planet. No, it was Maxwell, the guy from electromagnetism. That's right. Okay, he wrote the first paper on stability, and he won a prize of the Royal Society of London. Okay, and he was using arguments based on poles. He does not call it poles and so on, but he was using this argument. It was the first. You can, if you write Maxwell governors, Maxwell on governors, you will find this paper. It's readable. It's incredible. It's readable. But the first guys who started building this were using very naive arguments. But these naive arguments are important because they tell you, your intuition tells you that you are comparing Y with R. That's the big advantage of stability, of feedback. Now here, oops, I was advancing too much. Here, we don't have any comparison between Y and R because we have all this, we call it, let me use a strange word, paraphernalia, okay? And so it's a lot of stuff, okay? All this stuff. And then you are comparing something that is Y filtered by the estimator, the gain and so on. You are comparing it with the reference multiplied by a constant. Oh, okay, that's very strange. So one possibility is to rewrite these equations. I'm not going to do it here. I think it's again in that document. But anyway, Professor João Pedro Gomes will speak to you in the tutorials about the lab, in which you have a pretty much similar scheme, pretty much similar to the standard stability. So with amplifying, subtracting Y from R, and then amplifying the error with a controller. Okay, so it's also, so this is not the only possible problem. This is not the only possible approach to introduction of a reference. I'm not going to do it here. There is still another way of seeing the problem, which is I would like, okay, I'm imposing the poles of the system. Okay, and the poles of the system are the poles imposed by KC, because the poles of the estimator, they are imposed, but they are cancelled by zeros. This is something that we have not proved, but it's true. So you are imposing the poles, but you would like to impose the poles between the reference and Y and the zeros. Okay, so impose the whole transfer function, not just the poles. And this is something that we are going to study starting next week. Okay, so let's sum up what we have learned today. So yesterday we saw that by feeding back the state, you can impose the poles, provided that your state model is controllable. And today I presented to you two different ways of estimating the state, the predictive observer and the current observer. And then I said, well, there is something which is the separation principle, that if you, instead of feeding back the state, you feed back the estimate of the state, then you can design separately the gains of the controller that imposes the poles and the gains of the observer that imposes other poles related to the observer. And then I also said two important things. One is we can use the Kalman filter to compute the gain KO of the observer. So instead of imposing the poles of the observer error, I use an optimality argument. And this is the story of the Kalman filter. So in a sense, I'm optimizing the signal to noise error of the estimate of X hat. And I told you, well, you can use the MATLAB function DLQE to compute the gains of the Kalman filter. And the Kalman filter is nothing more than an observer, actually a current observer, with the gains optimized. It's nothing more than that. And then the other important remark is previously we were considering the regulation problem, that is to say, I want to keep y close to 0 no matter the disturbances. And you can introduce a reference in this way, as in this slide. And then I mentioned to you, well, there are two other ways of introducing the reference. One is by using the error between R and Y. This is not here. And the other is by imposing the transfer function between R and Y. Okay, this is what we are going to study starting next week. Any question? So if there are no questions, we will stop today here and see you or hear you next week. Have a nice week and good weekend. Bye-bye.
Thank you, Professor.
Thank you. Bye-bye.
Thank you, Professor. Bye-bye. See you next week.
Bye.